part 2, video cut. Okay, so you might not see this. Maybe I'll just, well, maybe you'll flip. Okay, so I was doing this, my video cut off, but anyway, at level 3, 3 times 3 is 9. You have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. Okay, and then it goes on and on. I won't go to all of it. 4s and 16. So you have 4s, 4p, 4d, and 4f. You have 7 4fs, 5 4ds, 3 4ps, and 1 4s. So all that adds up to be 16. So now the other thing. That's one little thing you should be aware. Now, there's something else not on your paper that well, it might come up later, but you need to know this as well. You should know that at any level n, this tells you how many orbitals there are, and total number of electrons. You can also get the total number of electrons, just multiply that by 2. You know, 2 electrons. 1 times 2 electrons is... So 2 electrons can be at level n equals 1. At level 2, you can have 2 times 4, 8 electrons. Because think about that. You have the 2s, you have 2 electrons. Then the 2p, you have 2, 4, 6, 8. 2, 4, 6, 8. You have 8 total electrons at level n equals 2. At level 3, you'd have 9 times 2, 18. At level 4, you'd have 16 times 2, 32. And you can trust that without having to go through. And you would just draw all the orbitals and fill in 2 electrons for each orbital. So it's a good, useful thing to know about that little n tells you how many orbitals. So if I wanted to say, yes, according to Schrodinger, orbitals go, even though, all right, here's your nucleus. Now, your nucleus might just be positive 1, like a hydrogen atom. And it can just hold 1 electron. Let's just say it has 1 electron that can jump up to where we said, like level, let's just say level 5. But then if you jump beyond that, then it'll be outside the atom. The atom will be ionized. It will no longer be H. It'll now be H plus 1. The electron has left the building. It is gone. Okay? So for hydrogen, the nucleus is not strong enough to keep it in like probably level 200 or something like that. But level 200 does exist, okay? So you have all these levels. The stronger the nucleus is, then the more electrons and more levels it can hold them into before they would leave the atom. But if I wanted to say, what if we went all the way up to level, 125, okay? Well, I don't know. I'd have to figure out what that would be. But at level 125, I know that there will be n squared. There'll be 15,625 orbitals at level n125 when I square it. And if I multiply times 2, that tells me I can fit 31,250 electrons at level n equals 125. So Schrodinger's equation just gives you the possibility at every energy level all the way up. All right, that's one little interesting kind of thing you should be aware of. And so, now I think I told you this, but now I'll say it again when I did electron configuration. But the S, P, D, and F, all of that was created to 1S, 2S2, 2P, and all that, 3S, 3P, 3D. That was created to make the quantum number system easier, to simplify it. So the original system was to all do it with quantum numbers. Okay, now, so let's move away from N. So N just tells you the energy level, which floor of the hotel the electron's on. That's the main thing. What does L tell you? L tells you, it has a name, and on your notes, it's called, sometimes they call this the orbital quantum number, but it's also called here's a weird one. Now, angular momentum quantum number, I don't hear that too much, but I really don't hear this one. Azimuthal quantum number. But it went the angular momentum or orbital quantum number. I like to call it orbital quantum number because it tells you which orbital. Now, here's what L tells you. L is equal to 0, 1, 2, or 3, and it can be any whole number. But I'll just show you how this works. 0, 1, 2, 3, and then there will be a 4, and it will keep on going on and on. I'll put a 4 there to show you. If L is equal to 0, then we say it is what's called an s orbital. If L equals 1, we call it a p orbital. If L equals 2, it's a d orbital. If L equals 3, it's an f orbital. If L equals 4, it's a g, then h, i, j, k, and it keeps on going. I don't know what happens when they run out of letters, or then they go like AA or BB or whatever, AB, AB, AC, AD. Just keep going forever. Okay, but anyway, okay, so what does it mean? This is a fun one that you need to kind of be aware of. In the atom, according to Schrodinger, remember I told you, it's like graphing a function, like y equals x squared minus 2 or whatever it be. I don't know how some function. It's been a long time since I did that in math classes. But okay, well, for this, all of these values, like say n, l, ml, ms, are like solutions, possible solutions you can get. So they call them a lot of times possible quantum numbers. So if L is equal to 0, that means it's an s orbital. And I'm going to try and draw a little s orbital for you. An s orbital has a spherical shape. Now, s spherical, I guess that's kind of a coincidence, but I'm going to draw a little circle. Now, it's not just a circle, it should be a sphere. Because you'd have an x, you'd have x and y, and you'd also have a z. Now, hopefully you've seen a z-axis before. But what that really means is you have like, well, I guess I could do it. I better not do it with chalk. I might break the chalk. Do I have anything around here I can use? Well, here are 2 pens. Ha! And here's a little chemical stirrer that I use. I can use that as well. I'll show you what I mean. Okay, yes, actually good. Okay, so x, y. That would be like x, y axis. Okay, x and y. But then z would be coming out towards you like this. So you can't really see the z. But see, if I turn it this way, now x, y, z. Oh, my hands are all in the way. I think you got the idea. But x, y, here, z will be perpendicular to y also. So there it is. Now when we draw these, like in the picture here, we do it like that. We kind of show it to you at this angle. Let me get this out of my hands. Maybe I can do it and show it to you. I think you'll get the idea. I do this with meter sticks at school. If I use less fingers, you might be able to see it a little bit. Let me put the red one there. Maybe you'll see it better if it comes out from the back. And let that one be the one that goes up. Oh yeah, that might be a little bit more clear. Yeah, I think you can see it. So I'm kind of doing something like this. The gray one doesn't hold up too good, does it? Okay, but notice this. I'm trying to make the x and y and then the z. So we're kind of showing it at an angle. It really is at an angle. That's why. Okay, hold on. Let me fix it. I can't. Either my finger's going to be in the way. There it is. I'm trying to draw it like that. So what you're seeing on the board should be x, y, z. Kind of not straight at you because then you wouldn't see it. But kind of like an angled off a little bit. Okay, here we go. So S, here is what I will draw. Now, I can't do a very good job of this with a chalk. I'm going to try. I'm going to have to erase some chalk on purpose here too. And I'm going to make it really dark in the center. Now, if you did this right, this would be a fun thing to do with finger paint. And my little kids would love doing that. Okay. But here's the idea. I'll just make it like that. It's not doing too good. This, all right, L value, according to Erwin Schrodinger, tells you the physical location, three-dimensional physical location where an electron in that orbital is most likely to be found. This is called an electron probability density cloud. Now, I use that long term because these are all the words I've heard them use, whether it's AP or AP books or whatever, or videos. Electron cloud is used a lot of times, the electron cloud. But the electron probability density cloud, that is what this shape is. Now, here's how I want you to think about this electron cloud. Now, at that level, it's supposed to be, first of all, when you see it darker, the darker area should be where it's more likely to find the electron. And of course, towards near the nucleus in the middle, around the center, that's where you're most likely going to find the electron usually. But it could be anywhere out as you move out, and it's less likely to be found as you go on the outside. So, I was trying to make it even lighter color. But electron probability density cloud, more likely darker in the center, and then as you go out like a cloud. Now, I mentioned this long ago, but I'll see if you remember. What you should really imagine is this would be the shape. I'll just draw the white circle for a moment. That's like the shape of where, I had some green on me. That is where the electron should be found, in this spherical region, okay? It will never be outside that region. But remember, the electron, if it's not moving, if you could freeze it, it's just one little baby speck. I'm going to have to try to erase all this stuff out of here. It's one little, look at that. I'll put one little baby speck. That's even going to be too big. There might be 2 electrons, maybe. So I'll put 2 specks. They could be in this s orbital. So L equals 0 tells you it's an s orbital. Let's just say it's the 1s orbital. So that means that n would equal 1 and L would equal 0. 0 is the name of the orbital. So instead of S, P, D, and F, we just say it's called an L equals 0, L equals 1, L equals 2, or L equals 3 orbital. Kind of boring, mathematical. That's why they made the little SPDF, make it easier. But here's another thing to think about. The electron, if you could just freeze it right where it was, it would have to be somewhere in that region. Now, most likely, the electron is going to be found, if you could freeze it and map out where it could be, it's most likely to be near the center. But it could be way out here. It could be all around, you see. And if you put all the possibilities, the cloud shows you inside where it's darker. Now, think about a fan that is turned off. And just say if you took off the fan blade, you only had one fan blade, like a propeller that only had one side on it. Actually, I've seen some of those before when they do, like they cut the weeds on the ground, like near a driveway, like a weed cutter, and it has like one little wire or something on it, like a plastic wire. But when they spin it around, you see like the design you see like with a fan, like with my hand. If I'm doing that real fast, if I go real fast with the hand around like that way, you'd see like. Where is your hand? I can't really do it that great with a hand. Oh, oh no, I don't want to hit myself with that. Where is the little piece that I was going to swing it around? Oh well, we get the idea. But as you swirl it around, this tells you like a fan where, as it moves around, where it could be. You can kind of see all the darker areas. Now, could you put your finger in there, in and out real quick and not get hit? Maybe, if you're quick enough. That's why I said earlier in the year, atoms are mostly empty space. If you only have one electron, if you could put something right into there real quick, you could like pass your finger like through the board or something. If you go through, but you have to have all the electrons have to be moved to one side. Almost impossible. But anyway, okay, back to this again. There is your s orbital, L equals 0. Now let's talk about the electron probability density cloud. Where is it likely to be found? And density just means it's going to be darker for the regions where it's more likely to be found. Okay, let's use an orange one for the P's. Okay, so for the P orbitals, I'll draw it up here. Now, X, Y, and Z will matter. And now you'll see, oh, okay. The shape of a P orbital. First of all, a P orbital is L equals 1 for a P orbital. Okay, and let's just draw the 2P. For the 2P orbitals, N equals 2, L equals 1. Now, the P orbital will look like this. I'm going to draw a single P orbital. Now, I'm going to draw it a couple of ways. I'll do it down here for the real way, I guess. A single P orbital looks kind of like this. Sort of has that shape. Now, that is only located on the x-axis. When I draw it, I usually like to draw it. It's okay to draw it that way, but I sometimes draw it a little bit more thin. Like a flower, pea, petal. Okay? That would be called PX. The PX orbital. Now, here's an interesting thing about it. Of course, it'll be darker near the center if I did it right. and it will be lighter in these areas. So I kind of erased that a little bit. I don't know. I guess I'm kind of doing decent of that. All right, but anyway, you can kind of get the idea. Darker here in this regions, closer, and outside it will be lighter. Now, a couple of things to tell you about this. These are called lobes of the p orbital. It has two lobes. They are not connected, though it might look like it here. They would not be connected. So they're separate. So what it means, in fact, in the middle, in between them, is what's called a node, N-O-D-E. A node would be between them. And remember, a node on a wave is a region where the wave is not moving at all, that is unchanged. Remember, if you're swimming, like a little baby duck swimming in the node between the waves, then you'll never feel the wave push you up or down or anything, okay? That's interesting. So now we're kind of getting to the weird science fiction kind of stuff of this. So the electron particle could be in this lobe, or it could be in this lobe. It could be in one or the other. It changes back and forth, and usually it's going to be around the center. It changes and fluctuates. When it does that, it is transitioning, or it is, what's the other word I wanted to use that? Transporting. How about that? So like matter, energy, kind of fluctuating. Energy, matter. It's like a wave. The wave, it's almost like saying a cell phone wave. Hey, I can pick it up, the cell phone, this frequency, I can pick it up here or here, but if I stand in the middle, I can't pick it up. I can't pick up anything because doesn't exist there. So the electron matter wave only exists in one or the other. Kind of a neat thing. Now, if you have two electrons, the two electrons might be here. Because remember, the px, I forgot to write that down, px orbital, 2 can be here, or 2 could be here, or, one could be there and one could be there. But it doesn't have to be this way. So you're not limited to that one lobe, okay? Both electrons. In fact, when we draw electrons in some models we'll see later, I usually just put them on the same side, meaning they can be on either of those lobes. All right, that's your px. So then guess what this will be? That's going to be your py. Uh-oh. I'm trying to not make a mess, but oh well. And it'll be darker near the center. I can't do it at all justify with this. Definitely look in your textbook and see the pictures of these. They're really cool. Or you can look online and see them. And then your PZ would be, one would be kind of going behind the board, and then one would be coming kind of out of the front of the board. Like a flower petal, you might say. So one back there, one back there. So you have your PY, your PX, and your PZ. Now, I told you that the real shape is a lot more round like this. And I can't really do justice to showing you this, but if I did one like that, and then one kind of before it and one behind it. Well, here's the deal. When you put together the PX, the PY, and the PZ orbitals, 1, 2, 3, 4, 5, 6. So 2 electrons can be in each one. 2, 2, and 2. 2 here. 2 could be in this one, either this node or this lobe or that lobe, or 1 or 1, or this one or that one. So you could have 6 total electrons. That's why we call it 2px, 2py, 2pz. Now, if you really drew them correctly, when you put together the x, the y, and the z all together, you're actually going to get a spherical shape like you see here. It's going to be pretty much a round shape. Not exactly. It won't be perfect. But it will be pretty much round. Like if you did with the balloons, it would be a lot better. And you may have seen that the UCLA program with blow up balloons. It'll become like, you'll see it like, it'll look really, really tight together, almost like a big circle. From a distance, to get closer, you'll see, oh, actually, there are shapes there. Okay, so, all right. So there's your P, X, P, Y. Now your d orbitals, they're going to be L equals, so 0 is S, P, D. L equals 2 is a d orbital. Now the d orbitals, it takes 2 axes to draw a d orbital. So a single d orbital. Now, again, I'm going to make these are usually a little bit thinner. They are a little thinner than the p orbitals. But that would be a d orbital. I didn't do a good job. It should be symmetrical. It should be a perfect, like, plus kind of sign. All right. And again, it should be, Oh, and I did the same color. Oh, whatever. Should have done a different color, but darker in the middle. Now, that would be called, since I use the X and the Y axis, that's called DXY orbital. Then you could do a DYZ orbital, a DXZ orbital. There's like 5 of them total. I don't remember all the names of them. But then there's a really weird one that is the DZ. Wait, oh, actually it's on here. Oh, I don't know if I can read it on my notes here. Is it the DZ squared? But anyway, there's one orbital. You can see them right here. There they are, the 5. They're green on this paper. But look at that last one. How bizarre this shape is. It's just kind of neat to look at it. The last one has a shape that looks like this. And we should tell people D like a donut. It looks like there's a circle. I'm not doing at all justice to this. It is a circle, if you can see from like the top level. But I want to make it more flat. So there's like a circle, like a donut. Then you have this sort of like lobe above and below, like that. Like a teardrop kind of thing below and above it. How weird is that? Okay? Bizarre looking stuff with a circle right there. You can kind of fit them together. That's one of the d orbitals as well there. So anyway, I'm not going to make you draw these. No. But they have shown you shapes before. You should know at least know, okay, I'll take that back. You should know how to draw an S and the P, X, Y, Z, but not the Ds. I could say draw a single d orbital, it would look like that. All right, so now let me show you one more thing with these orbitals. Oh, and I'm going to have them. Oh, no, it's not too bad. I'll say I'm going to have a mess on this chalkboard while I'm trying to erase all this. Okay. All right, so here we go. SPDF. All right, so this is something that a teacher showed me before as well. I'll try hard to do it. Let's see if I can draw this on the board. I better erase a little bit more of that and show you up here. Yeah, I'll do it this way. All right, so first, what I'll do is I'll just start in the middle. Can you see that line? Yeah, you can. Oh, I'll just use this line. I'll use that line. It's going to probably run off the board. Yeah, it will probably run off the board. But I'll try. Oh, well. I'll start off. First, I'm going to draw just a 1s orbital. So 1s, at the first orbital, you have this. And it will be a spherical shape. Okay, 1s. Then the 2s orbital, we know that the 2s orbital is going to, on the average, it should be a little bit farther away. I guess I could use another color. Just to, whatever, play around with it. It should be a little bit farther away from the nucleus. Because, remember, think about this. The 1s electrons, the 2, they take up space. I mean, this might be almost the size of 2 electrons that I drew there. So this would be really, really small. And you know that in some sense, we know that they're fluctuating, transitioning through this like matter, energy. So they can interfere with each other, negative. Well, the 2 electrons that are inside here have opposite spins. We mentioned that. Okay, but anyway, look at 1s was the white one. But the 2s would actually include all the 1s region and a little bit of region outside of that. So your 1s will be the inside ring. Then you have another ring sphere around it. So what that tells you is that just like 2 radio stations, you could have one radio station, 101 could be on right now, and another person in the same place, you could also have like a 105 at the same time, the same exact position. Those 2 stations are going through each other, waves, but they're not interfering with each other because they're on different frequencies. Well, kind of like different planes of existence. 2 electrons are in the 2s, and the 1s could like go right through each other and they wouldn't interfere if they were completely energy. But now they're not completely energy. They're also matter, and they're kind of and they're fluctuating. Their speeds can change. Their levels can change when excited state and ground state and all that. So anyway, somewhere there has to be some kind of like middle ground. But we imagine that the electrons in 2s are going to be a little farther from the nucleus than those in 1s. Okay. Now, what about 3? So let's go to level 3. So we have 1s, 2s. Now, also you have 2p. I better draw 2p. So 2p, I'll draw it this way. So I'll just say, here's a 2p. Oh, they're not doing that big. Sorry. Here's a 2px. Here's a 2py. I'll make it more flat like that. Yeah. Okay. All right. And so all of that would be your 2p. And then 2pz would be in front of it here as well. So 1s, 2s. So you see, in the 2p's, you're a little bit farther from the nucleus. And I'm probably overdoing it a little bit. I should make these a little smaller. I really should make it smaller, but I'm kind of exaggerating it. Next, I'm going to draw the 3s. So 3s would be like just a little bit above here. Oh, this chalk is not liking this. So 3s would be like that. And again, 3s would include everything in this same region. So see what I mean? Now, 3s electrons will usually be farther away from the nucleus than the ones that are in 1s, because 1s are stuck inside here. So for sure, 3s are farther away. But it is possible a 3s electron actually could be here. There could be a moment where a 3s electron could be closer to the nucleus than a 1s electron at a given moment. But for the average, most of the time, it'll be farther away. But notice this 3s electron is really close to the 2p. These are not too far apart. The energy, I mean, well, that's not really true. That could be in here, but I'll just say that a 3s, I just did two little yellows. That's in the 3s, and that would be in the 2p. And look how close together they could be. I mean, they could be. Now, again, the 2p is most likely to be more near the center, but it can be. But on the average, okay, that gives you an idea. So 1s, 2s, 2p, 3s. Then you get your 3p. And so for 3p, I'll try to continue that on real quick. So it'd be more like, I'll try to make it a lot more flat if I can. Something like that, or I'm trying to make my little, I'm not doing a great job of that one. Oh well, we'll just kind of show you. So here's like the 3p. Oh boy. But now, let me show you something, and this is just based on the shapes. This might also be a way to explain something that happens in the electron configuration. What comes after 3p, then you get you get 4s, yeah. So how about I'll use, if I use green, did I ever use green? I don't even remember. I guess I didn't. So now I'll just draw the 4s. The 4s will now just go around here. And notice this. All right, the 4s. Oh, I forgot to draw my 3D. I'm sorry. I should have drawn the 3D first. I'm just playing on the board here. I'll draw a single 3D. Yeah, that's probably a better way to do it. It's going to be a mess. But anyway, a single 3D is a lot like a 2x, 2px, 2py. Okay? But there's your, I should have done, we'll let the D be another color. I should have done a different color, I guess. Maybe I should have used a purple, right? I don't know if that's going to show up. All of this should be a single orbital for your 3D. All right. Now comes on green the 4s. And that's why I wanted to show you. If you go over here, all around it with the 4s. Haha, what a mess this is. So the green, and of course it will include everything all the way to the nucleus. If I do the 4s. If I made a cloud, I'd have to cover all this up. But look at this region here. Maybe, just maybe, and it's more like my drawing too, but if we could build this out of like balloon or something, there is some space, some area in here where this is only 4s. This is only 4s. Oh, maybe that right there, yeah, because there's one right there. This is only 4s region, but notice you also have your 3D right there next to it, your 3Ds and your 3s. So that shows you why these are very, very close in energy. Why as you're building up Hog Hotel and you're putting all your electrons in, the electrons can say, after I fill up 3p, all these electrons, all this negativity is building up. Well, even though 3D is closer to the nucleus than is 4s, they jump out and they fill up the 4s regions first. I mean, it's just my drawing, just kind of my little idea, my theory. Hey, maybe the 4s has some regions, has like, hey, I can go in there, the Hog Hotel, the negative, and I'll stay away from other electrons in the 4s. I can kind of be in this little region and spend more time there. I don't know. There could be some truth to that. So anyway, but it tells you, kind of tells you how the orbitals all put together. All right, how all this craziness. Now, I am now about to move on. Let me see how my time is looking, if I need to make another video or not. Yeah, I guess I'm going to have to make another part video. Okay, well, I've told you about L and N. In fact, let me tell you one more thing about L. Now I'm getting into the you don't need to know this part, bonus material. But if N, for any level N, L will always equal any possible number from 0 all the way up to N minus 1. This is a formula. You don't have to know this right here. It's old. It's in the textbook. It's a bonus material now. Okay, I'm getting into the bonus. But I'll just say this one, then I'll go on the other video. I'll do the other. So if you're at level N equals 1, that means L can only be N minus 1. 1 minus 1 is 0. If you're at level N equals 2, L could be N2 minus 1 is 1. It can be any number. Here it's only the set of 0. Here's the set of 0 or 1. If N equals 3, L would be any number in the set of 0, 1, to 3, N minus 1. 3 minus 1 is 2. So what does this mean right here? What in the world am I talking about? Okay, it tells you about electron configuration. At level 1, you can only have an S, 0. At level 2, you can have an S or P. At level 3, you can have an S, a P, or a D. And so it tells us what rooms are available on each floor. You have a 1S, you have a 2S, and a 2P. And then the third level, you have a 3S, a 3P, a 3D. Aha! 3 orbital. This tells you the wings of the hotel. Now, of course, if I go to any P wing, there'll be 3 rooms there. If I go to any D wing, there'll be 5 rooms there. Any S wing, there'll be only 1 room. And each room, or each orbital, holds 2 electrons. So the rooms are orbitals. Okay, and then in 4, you'll have 0, 1, 2, 3. You have 4, S, P, D, F, and so forth. So there's a little... So it's kind of like, as I was telling you, this came before electron configuration. And you can kind of see, oh, it's better that they made electron configuration to simplify it. But you know what's really cool? And I'm going to show you this. I could almost do this so quick. I don't think it'll take me that much more time. I don't know if I've got a minute. I better just wait. But with quantum numbers, you're able to... Here's what I'll tell everybody. Look at all the electrons in the hotel. Okay? Let's just say you're going to have a party and you want to invite all these hogs to come to the party. But you say, you know what? There's only certain hogs I want to invite, not all of them. Well, every little hog in the hotel has its own address. Its perfect own address. You can write a letter, an invitation, and send it. If I only want to send it to the 3S hog on the bottom bunk, I have a way with quantum numbers to identify and get the address of that electron on the bottom bunk. Okay? And I'll do that in the next video. But I'll show you quickly a little bit of it, and I'll talk about what it means. The address consists of N, L, something called ML, and MS. And I'll tell you this if you're interested in the next part of this. Like if I have an electron in the 3S, and I want the down electron. What is the down electron? That down electron. Well, the N value, what floor of the hotel? It's on floor number 3. L tells me what wing of the hotel is it in? Is it in S, P, D, or F? Well, it's in an S, and you need to remember for that, L equals, well, I'll put it up here. L equals 0, 1, 2, 3, S, P, D, F. So L, if it's in a 3S, L equals 0, okay? So if it were a 3P, then L would equal 1. I'll show you that on the next. But anyway, we got 2 of the letters in the address, and I need to tell you about these 2. And then you'll know all of the quantum numbers. Okay, I'll see you guys, and I'll have to do that in another section.